Hello everyone, and welcome to AP Chemistry Unit 1.2, all about mass spectroscopy. But what is mass spectroscopy and why do we need it? In this video, we're going to quickly review isotopes and atomic masses, and then we'll talk about what mass spectroscopy is, how it works, and we're going to interpret the data that it comes up with. And finally, we'll look at a few AP-style multiple choice questions that deal with isotopes and mass spectroscopy. So let's get started. The atomic mass on the periodic table is supposed to show us the mass of one atom of each element in atomic mass units, which is to say the sum of its protons and its neutrons. But you've probably noticed that most of them on the periodic table have weird decimals attached to them. And how does that make any sense? Because how can you have like 0.97 of a proton or a part of a neutron added up? It's either one or zero, right? Well, we have to talk about where this number comes from and how do we actually know this number. And in order to do that, we'll do a quick little review of isotopes. I will say that in the playlist, there are several videos about isotopes, starting with the very beginning and working up through isotope notation and things. I'm going very quickly on that today so we can get to mass spectroscopy. So for example, easy example, carbon, there are 3 versions of carbon. They all have 6 protons. That's what makes them carbon. But some have 6, some have 7, and some have 8. In fact, the vast majority of them have 6, but they're the few with the other 2. Carbon 13, 12, 13, and 14 are their names. And if you need a refresher on that, please check out the other videos. Just giving examples here. Potassium has 2 naturally occurring isotopes. There are 2 versions of it. Both have 19 protons. One has 20 for a total of 39. One has 21 for a total of 40. So 2 different masses, but they're the same element. And in fact, I won't get into it on this video, but I made a video about how isotopes were discovered. And in it, we mentioned that isotopes, the word isotope means in the same place. They have different masses, but they have one box on the periodic table. So we have to come up with a mass to represent both at the same time. All right. Quick side note into isotope notation, in case you need a brief refresher, because you'll see a few of those. Isotope notation contains the element symbol, the atomic number on the bottom, and that should be the same for each isotope of every element. The mass number goes on the top, so like carbon 12 would be on the top, carbon 13, carbon 14. And if there's a charge where it's lost an electron or gained an electron, that would go there. So some examples might be the 3 isotopes of hydrogen and, of course, the 3 isotopes of carbon in isotope notation over here. So just for fun, let's review that. We'll do it quickly. Let's write isotope notation for the following. Magnesium, 25. I'll do a couple. I'll have you try a couple. Magnesium, 25. So first, what you want to do is get the element symbol in there. Okay. On the bottom is its atomic number. On the top is its mass number, and that's what's given here. In the name of the isotope, that's the mass number that goes on top, so 25. So I would recognize that there's 13 neutrons in there in addition to the 12 protons. Bromine has the symbol Br. Its atomic number is 35. Now, unless you have your periodic table memorized, you're going to have to go and look for it and find out that it's in box 35. But the top part is given for us if we know what to look for. So let's put that in our isotope notation. Okay, pause the video a moment if you'd like to try the next 2 and see how good you are, and then we'll move on into mass spectroscopy. Okay, and if you came up with those 2 symbols for chlorine and zinc, 37 and 66 respectively, then congratulations. You have mastered isotope notation. So where does this number on the periodic table come from that we put in each box? Well, the atomic mass on the periodic table is actually a weighted average of all the naturally occurring isotopes of the element, or the masses of them. A weighted average takes into account not only the masses of each isotope, but also the percent abundances of each. Percent abundance is that percent of all the atoms of the element that are that particular isotope. Okay, So there's a formula for this. You may want to pause the video and write it down if you haven't yet or don't have it in your notes. The atomic mass is calculated by taking the mass of each individual isotope, like the mass of isotope A, first one, times its percent, plus the mass of isotope B times its percent, and so on for every isotope of that element. So if it has 6 isotopes, you got to do this 6 times and add up the results. Quick note, percent values should be entered as decimal form. So don't enter 24.83, you would enter 0.2483 if you were calculating it. Now, I haven't seen many questions where you're actually calculating it, but I've seen questions where you need to know how it is calculated. So for example, chlorine, there's 2 versions of chlorine, chlorine 35 and chlorine 37. They don't exist in a 50-50 ratio in nature. Turns out the chlorine 35 is much more abundant than the chlorine 37. It's kind of like if you just started separating them and made little piles, the pile for 35 would be 3 times as big as the pile for that one. Just the way it is. No rhyme or reason. It just happens to be that way. So the atomic mass is not 35 or 37, but it's 35.453 because we take the mass of one, the exact weight, times its percent, the exact weight of the other one, times its percent, and multiply it and then add it, and we get this answer, 35.453, which is the number on the periodic table. Now, I know what you're thinking. How do we figure this number out? How does anybody know that 75.77% of all chlorines are that one and not the other one when they're so tiny you can't actually even see them? And how am I supposed to make little piles and separate them? That's a very good question. And that brings us to mass spectroscopy. Mass spectroscopy is, in my opinion, a miracle of modern science developed a little over 100 years ago. Mass spectroscopy works on the principle that heavier objects are harder to deflect than lighter objects. For example, and just go with me here, if you were to throw a ping pong ball at me, I would have very little difficulty deflecting that ping pong ball because there's not a lot of mass there. But if you were able to project a bowling ball at me, I would have a much harder time trying to move it from its trajectory, right? And the same goes with atoms. Yes, they're tiny, but they have different masses and so different abilities to be deflected by, in this case, a magnetic field. So a mass spectrometer essentially works like this. You take your sample that you're interested in, your element, your chlorines or whatever, and you vaporize them so they're all separate from each other. And then because a lot of them are charged, you can actually use magnets to speed them up like you're throwing them, and then use other magnets to try to deflect their trajectory. The ones that are lighter get deflected more, the ones that are heavier get deflected less. And if you have an electronic detector somewhere at the end, it can tell which ones are actually, it'll detect a stream of ions and isotopes and count them by the little electric pulses that it gets. You get a graph that looks something like this spit out at the other end, and this graph gives a lot of information. Okay, this graph here is the graph for neon. Okay, we learned that there are 3 isotopes of neon because there's 3 different beams that they're deflected by, and 3 different peaks with 3 different heights attached to it. And what this graph tells us, this is a mass spectrograph, is that it tells us, A, that there are 3 different isotopes because there are 3 different peaks. It also tells us that peak A, the one at the 20 AMUs, is the most abundant. And so if I add up the total area of all these peaks and then take this one divided by the total, I'll get a percent and say that's the percent of neon 20, that's the percent of neon 21 and 22. So that's what you need to remember about a mass spectrograph. It gives you a peak for each isotope, and the height of the peak represents how many of that isotope it is. Okay, so we're going to look at a couple of mass spectra here. Ignore these 2 at the end. Those are just the scales up to 100% and so on. And you look at the scale down here, 46 up to 58. You might be asked questions. First of all, how many isotopes does this element have? We're not told which element it is, but I can tell you that there's 1, 2, 3, 4 isotopes because there's 4 peaks, 4 beams inside the mass spectrometer. I can tell you that isotope number 52 is the most abundant because that's the tallest. The question you're most likely to be asked is, which element is this? Okay. And in that case, you have to go to your periodic table. You'd have to find it. And what you're going to be looking for is an element such that, and you can check your work, you can do the math if you want. Take 50 times its percent, 52 times its percent, 53 times its percent, and so on. Or if you're running low on time, like you would be on an AP exam, you look around for an element whose mass is somewhere between 50 and 54, because that it has to be, it's a weighted average. But because it's a weighted average, it's going to be really close to 52. Okay, so you're going to scan your periodic table for something very close to 52. And in this case, I'm like 47, 51. Here's, 51.996. That one is very close to 52. And so my guess is that that is the mass spectrum for chromium. Let's try another one. Here's another one. Again, ignore the end ones here, but you'll see peaks at 108, 106, 108. That's 2, 3, 4, 5, 6, 7, and 8 peaks. So there's 8 isotopes for this element, whatever it is. Number 114 is the most abundant. Okay. But there's also a pretty abundant one here at 112 and 110 and 111, kind of a in here, something in there. So if I'm trying to identify the element, which is your main task, I think, I'm looking for something with a mass between 106 and 116, but somewhere in this range in terms of its weighted average mass. Again, you could do all the math and check it out, but if you scan your periodic table, you can find, let's see, we're here at 102, 108, 6, 108, 112.4, which is right smack in the middle of those peaks, and now we're at 114 and moving up further. So I'm going to guess cadmium on that mass spectrum. And now let's wrap things up by looking at a few AP-style multiple-choice questions in regards to isotopes and mass spectroscopy. Let's start with the easiest one of the group. A monatomic ion contains 15 protons, 16 neutrons, and 18 electrons. What ion of what isotope is this? So here we're building an isotope using the material that we've been given. So first I notice it says 15 protons. That tells me that it's element number 15, which is phosphorus. Okay? And that leads me to A and C. You can check your periodic table too. Phosphorus is number 15. Then it's got a total of 15 protons and 16 neutrons for a total of 31 atomic mass units. That means I'm looking for phosphorus 31. And it turns out both of them are phosphorus 31. Okay? And then the last part is we have 18 electrons. This is an example of an isotope that has gained electrons, whereas it would have started with 15 as a neutral atom, but now it's gained 3 more to make 18. And you might know that when you gain electrons, the isotope becomes more negative. So I have a choice of 3 positive or 3 negative, and I'm going to go with 3 negative because it has gained those electrons. If you have questions about that, you can refer to the beginner isotope videos farther down the playlist, not labeled AP Chemistry 1.2, but part of the isotope series. All right, let's crank it up a notch. Not in terms of difficulty, but in terms of the density of times you actually have to do this. Which pair of atoms represents nuclei that have the same number of neutrons? Okay, different isotopes may have the same number of neutrons, but they have to have different numbers of protons if they're the same element. So in order to do this, we will have to take the atomic mass number, in this case 56 or 58, and subtract the atomic numbers for each of these isotopes to decide how many neutrons each one has and which pair has the same number of them. For example, cobalt is element number 27. That gives me 29 neutrons. And cobalt is also number 27, so that gives me 20 or 31 neutrons. Okay, sorry, the math wasn't mathing. And so I can tell they're just 2 different isotopes of the same element. That's not going to work. Manganese and iron, both at 57 each. But manganese has 25 protons, iron has 26. If you subtract them both, you get a different value. The one that gives you the correct value is D. Nickel is element number 28, subtracting gives you 30. And cobalt is element number 27, subtracting again gives you 30. So these two have the same number of neutrons. Not hard math, But, you have to do it a bunch of times for a multiple choice question like this. Okay, next one. This gets at the way we calculate weighted average atomic mass. You kind of have to know that formula exists or that process. You don't have to memorize all the AMUs and percentages. Those should be given to you. For example, naturally occurring copper is composed of two isotopes, 63 and 65. If copper is 69.1% 63 and 30.9% 65, the average atomic mass would be estimated as, and here's where you just have to know the formula and plug it in. So we need the weight times this percent plus the weight times its percent. The catch is that percent has to be in decimal form. So we have to match up the 65 with the fact that it's 65 is 30.9%. So I need 65.309 and 63 times 0.691. And we don't have to divide it by 2 like you would in a normal average. So we're going to stop it at letter C. And finally, let's look at some mass spectrums. And you can see this one. This one might look familiar to you. A mass spectrum of a naturally occurring sample of an element is shown above. What is the element? Well, you could say, well, we have to find an atomic mass between 20 and 22, but that's going to be really close to 20 because that's the one that's most abundant. And you might also notice that this one appeared in our picture of the mass spectrometer, and it is neon. You can check your periodic table. The mass of neon is 20.18. Next one, typical question. Name the element whose mass spectrum is shown above. Okay, here we go. We got isotopes 32, 33, and 34. 32, 33, and 34. 32 is vastly more abundant than the other two. And so I'm looking for an element whose weighted average is between 32 and 34 and very close to 32. And that turns out to be sulfur at 32.066. All right, finally, here's another one. The mass spectrum of a naturally occurring element is shown above. What's the element? Take a moment, pause the video, and see if you recognize this one. And if you recognize these numbers as being eerily similar to a previous slide, 35 and 37, 35 being more abundant, this is most definitely chlorine, which clocks in at about 35.453. All right, and we're almost done. And you might be wondering, hey, Mr. Rudolph, this is the same mass spectrum. And yes, that's true. It's a different question. It's more of a free response type question. But it says, identify the element, explain how it supports your identification, in which case you would say the atomic mass of chlorine falls between 35 and 37, but more toward the 35. So that's evidence. This one also includes something about PES. And now what is PES? That is something short for photoelectron spectrum, which is not the subject of this video, but it will be covered in a later video, so you can get excited about that. Well, I hope you found this helpful. And if you have any questions about mass spectrometry, you can send them to me in the comments. And in the meantime, happy studying and have a great day.